Assalamualaikum and good day everyone. Today we will proceed with the next chapter, that is Alkyl Halide. So alkyl halide is basically an alkyl connected to the halogen atoms. Alkyl halide can be classified as methyl halide, where halide is attached to a methyl group, primary alkyl halide, where carbon to which halogen is bonded to attach to only one other carbon, secondary alkyl halide, as well as tertiary alkyl halide. I always simplify classification of alkyl halide that can be used as well for classification of alcohol, as well as later classification of amine. They will follow the same principles. So, for example, I have tertiary, secondary alkyl halide, and primary alkyl halide. So very simple thing to note is that aside from the previous definition, you can also like my own kind of way to classify them using a very simple derivative such as this. For example, I take X. X can be any halogen atom such as bromine or chlorine or iodine. Alright, so this one we have, for example, I'll give you just straightforward example so that you can compare them straight to the real example instead of seeing a theoretical example. Okay, so alright, now this one is CH3CH2Br. Okay, essentially for the first or the primary alkyl halide, you will see where is your carbon that attached to the halogen atom. And from there then you clarify or classify them, see whether how many hydrogen does that carbon with halogen atom has. Okay, for example, the primary, you can see that the carbon that attached to the halogen atom, okay, the carbon that attached to halogen atom, now to be fair, I'll make all of this as bromine so that you will see instead of having X, okay? So you see the carbon that attached to the bromine atom has 2 hydrogen, okay? When that carbon has 2 hydrogen, then that is primary alkyl halide, okay? When that carbon that attached to the atom, bromine here, has only 1 hydrogen, that is secondary. However, when that carbon with halogen atom doesn't have any hydrogen, then you may classify them as tertiary. For alkyl halide, for the purpose of alkyl halide especially, it is very important for you to be able to classify them into primary, secondary, and tertiary alkyl halide, because the differences in classification of alkyl halide will result in different mechanism that the alkyl halide will take part in. Okay, so to to simplify, I would say, so this is my kind of way, is sort of the definition by theoretical. So you see the carbon with bonded to any halogen atom, okay, this one has no hydrogen, alright, this one has 1 hydrogen, this one has 2 hydrogen, okay, so to simplify things, alright. Now, we can also classify the alkyl halides according to these differences, this different type of class. Alkyl halide is a halogen is directly bonded to sp3 carbon. Vinyl halide is halogen is bonded to an sp2 carbon of alkene. So you can see there's presence of alkene. Now, aryl halide is halogen is bonded to sp2 carbon or a benzene ring. Now, IUPAC nomenclature. This is very important and crucial part of alkyl halide for the naming. Okay, the alkyl halide sits below alkane in the term of priority. Therefore, they will be named as haloalkane. Now, the principle is the same as, like alkane naming, for example. You choose the longest carbon chain. Even if the halogen is not bonded to any of those carbon, choose the longest carbon chain. Then use the lowest possible number for the position. Okay. For example, you have butane here with chlorine at carbon 2. If you see here, the numbering is slightly wrong, okay? So you place number 1 here, number 2 here, alright, number 3 and number 4. Remember, organic chemistry always prefer the lowest number of carbon possible. So that is applicable for the naming of this particular compound as well, where chlorine, instead of sitting at carbon 3, we will, if carbon 3, what I mean by that is when you read from right to left. So when you read it from left to right, this particular carbon will be named as carbon 2. Okay? Now this one is a bit quite different, where we have tackled this in the naming of complicated substituent in the nomenclature of alkane. Previously, you may look at previous example of naming complicated substituents, complex or complicated. Now for this one, you can see that our longest chain, again, the numbering is different. It's wrong here. Okay, we have carbon 1 here, 2, 3, 4, 5, 6, 7. And some may ask, Doctor, why is it not numbered from right to left? If you number it from left to right or right to left, because we have 7 carbons. So essentially the carbon that will be placed with the substituent is at carbon 4. Alright? Now, at carbon 4, however, we don't only have ethyl. At the ethyl substituent, we also have the presence of halogen atom, in this case, fluorine. Therefore, we have to, this is like inception if you recall my explanation earlier. It is a substituent in a substituent. Okay, now fluorine here is a substituent for the ethyl. Okay, fluorine here is a substituent for the ethyl, not for the entire heptane. Therefore, you have them in a bracket, whereby we have the whole thing as substituent at carbon 4, and ethyl is the ethyl fluorine is present at carbon 2. Now for the substituent, you don't follow this principle. Okay, even though fluorine sits on the carbon at the end, you don't number them as carbon 1 over there. You have to number them as the closest to the whole substituent that we have. Therefore, this will be numbered as carbon 1. Okay? So these are further examples. You can see here, when we have 2 types of substituents, bromine and methyl. So in this case, you will have to follow alphabetical order. Now, to which one to prioritize in terms of naming? So, of course, you will prioritize at the lowest number of carbon possible. Again, this is 2, 3, carbon 4. Now, this is carbon 5, carbon 6, carbon 7, carbon 8, and carbon 9. Okay? So, if you number them from right to left, bromine will be present at carbon 4. So accumulatively, the results between carbon 4 and carbon 8 will have 12. But if you cumulate carbon 2 and carbon 6, what I mean by that is here, if from left to right, therefore it will result in lower cumulative numbers. So therefore we will choose to number them from left to right. Okay, even very simple, you can see that the first priority present, if left to right, is carbon 2, right to left is carbon 6. Okay, now this one is the one with when we have alkyl halide with additional presence of stereochemistry. In this part is geometrical isomer, which is cis. So we have cis-1 bromo 3-fluorocyclohexane. To choose them, basically bromine and fluorine is both halogen atom, so we will follow the priority for alphabetical order. Okay. In addition to the IUPAC naming, you may also what we call as systematic common names, where instead of having alkane at the end, we use halide or halogen as the suffix for the name. Okay, and it is useful only for small alkyl group. But remember, if the assessment or the question want you to name them according to IUPAC, then you will follow the previous naming. Okay, so if say you want to name them just for the common name, you can, for example, over here we have isobutyl bromide, we have sec-butyl bromide, and we have tert-butyl bromide. So from here also you can see that this is tertiary alkyl halide. This one is, what is this? Secondary alkyl halide with one hydrogen. This one is, you can see at the carbon attached to bromine, this is primary alkyl halide. This is a perfect examples of classification of alkyl halide. Now, other common names of halide. Okay, for example, we have CH2X2 atau Cl2 is called methylene halide. So CHCl3, for example, is a chloroform. Okay, if you find trichloromethane in the lab, for example, in my own research lab, you can find trouble to actually find trichloromethane. But when you say, I want a chloroform, so everybody knows chloroform. So that is like a commercial name for trichloromethane. We also call CCl4 instead of tetrachloromethane, we call them as carbon tetrachloride. In fact, for CH2Cl2, we don't call methylene chloride in the lab. We call them dichloromethane. Okay. So we have two types of dihalide: geminal and vicinal. So geminal is when two halogen atoms are bonded to the same carbon. Okay, bonded to the same carbon. Vicinal dihalide is when two halogen atoms are bonded to adjacent carbon. What do you mean by adjacent carbon? Adjacent means sebelah or neighboring. So geminal, when you have two carbon, the halogen present here at the same carbon. Alright, however, for vicinal dihalide, the halogen present in the adjacent carbon. Okay. Now, the next one, we will look at the properties of alkyl halide. We have greater intermolecular forces, higher boiling point. Okay, so two types of causes for these differences in boiling point. One is dipole-dipole interaction and London forces. Okay, as well as spherical shape. Spherical shape decrease in boiling point. Very simply, greater mass, higher boiling point. Okay. Now densities, you can see that alkyl fluoride and alkyl chloride are less dense than water. So all alkyl bromide and all alkyl iodide are denser than water. Now we will look at the synthesis of alkyl halide. So there are various ways to synthesize alkyl halide. The first one is what we call as halogenation of alkane, something that you have learned in the topic of reactions of alkane, okay, whereby it involves free radical mechanism, something also that we have looked at, where reaction produces a mixture of halides isomer, products were separated to dissolution products. So example given here is from the reaction of methane to chlorine. And you have to remember, for the reaction of alkane, you have to make sure that there will be presence of lights or heat. Okay, in this case, we can use H mu that represented the lights. Okay, so the first product that you've got is first halogen substitution. For example, in the case of isobutane, you got tert-butyl bromide. You may want to look back to the reactions of alkane that involve halogen, okay, and the results will be the same. Now, you have to see this further example, halogenation of alkane. You can see that in the reactions of chlorine with the presence of H mu to cyclohexane, we will have chlorocyclohexane. And then reaction for butane, isobutane with bromine, in the presence of H mu, we will get third butyl bromide. In addition to that, we also have to look at this in the reactions of alkene. You can see the previous example in the lecture notes as well as the live video for halogenation of alkene. We can have two types of halogenation. The first one is addition of hydrogen halides to alkene, where this reaction are controlled by Markovnikov rule, something also that we have looked at, where very simply you can see or read this further explanation, but my kind of explanation is very simple. Hydrogen will be added to carbon with more hydrogen. That is essentially what you need to know. Hydrogen will be added to carbon with more hydrogen. For example, in this case of propene here, we have this carbon, okay, with one hydrogen, and we have this carbon with two hydrogen. Because of that, now, with the principle of adding hydrogen to carbon with more hydrogen, if you don't want to summarize them into 3 hydrogen, you may want to use this as 2, and then you add hydrogen here. Then bromine will be added to the middle carbon. Another way to halogenate or adding halogen to alkene is using a dihalide. Okay, for example, you may want to use bromine or chlorine. So in this case, if you do a direct comparison to halogenation of alkene, we no longer need the presence of H mu. Okay, where this reaction will proceed straightforward. We don't need to use Markovnikov rule or anything like that, because it is a very simple reaction where you will add 2 bromo or 2 chloro, whatever halogen that you use, to both the carbon that involve. Always remember, whatever reaction that will take place, this will be applicable to all types of reaction. Reactions will only occur at the carbon with the functional group. For example, if we have carbon-carbon double bond here and here, so any reaction will be proceed there. Okay, there will be no reaction that will take place in the carbon with no functional group involved whatsoever in the reaction. Okay, so this reaction will produce vicinal alkyl halide, where substitution will take place at adjacent carbons. In addition to that, we might also use or halogenate alkene through what we call as allylic halogenation. There are 2 ways that you can use that. First one, so where instead of having the substitution or addition at the carbon-carbon double bond, we now add the halogen atom to the carbon next to carbon-carbon double bond. Alright, where we will call them as allylic position. Alright, alkene can be directly halogenated in the allylic position. So for the case of chlorine, we can use high temperature and lower concentration of halogen used to prevent reaction at double bond. So for example, here we have cyclohexene reacting with chlorine. So you see there's, instead of having no condition mentioned in the reaction, for example, in the previous one, you can see in the bromine, so there's no temperature mentioned here. This one we will mention that reaction will take place at very high temperature, 400 degrees Celsius, and instead of having the reaction there, so the reaction will be added to the adjacent carbon. This is a very special interaction or reaction that you can accomplish. Another way to do this is what we call as NBS. So when you are writing the reaction, you don't need to write the chemical compound. Okay, it is sufficient if you just wrote NBS, and then it's understandable that the reaction will take place at the carbon adjacent. So there will be no reaction here. So we will maintain the alkene group there, but the carbon next to the alkene group will have addition of Br. So if you use NBS, you cannot have Cl as the carbon next to double bond. Alright? So NBS, why only Br substituted there? Because the name or the compound only consists cis of bromine. So its full name is N-bromosuccinamide. Okay, so this is a further explanation for the allylic bromination. You have allyl position, okay, in the example of cyclohexene, okay, where allylic hydrogen will be substituted. Okay, so if I may add here, you can use this one as, for example, H mu actually showing that it is with heat. All right, okay, it is with light, and you may want to replace this with 400 degrees Celsius, or instead of having Br there, you might want to use straightforward NBS, and we will get the same product. So reaction mechanism is quite similar to reaction mechanism of alkane reaction with halogen, where we will have radical reaction. Okay, so this mechanism involves an allylic radical stabilized by resonance. If we want to recall, radical is different than electron, where electrons always and only occurs in pair. Radical only occurs as one, so the electron has been separated. That's why we will call them as radical. So this mechanism involves allylic radical stabilized by resonance. So every time you may want to refer this reaction mechanism to alkane reaction mechanism for halogenation of alkane. The radical in Br will react with one electron from hydrogen. Therefore, we will form a radical at this carbon. Okay? Then that radical from that carbon will merge with another radical of Br, and you will produce this as the final product. Okay? So this is another example of halogenation with MBS. Previously, we have looked at examples where we look at example of cyclohexene. So if you see, when we talk about this, we only look at cyclohexene. And is that only applicable for cyclohexene? It is not, because you may have a straight chain like this, where we have 2,3-dimethyl-butene, okay, and we react them with MBS. We will preserve and maintain the CC double bond. However, now we are going to add the Br to the adjacent carbon. In this case, because it is quite stable, so we have all CH3s and CH3s. So now the Br will be substituted at one of the CH3, and we will got this as our final products. And you see, we have given another options here. So essentially, I think this is the one that we want to look at. Okay. Now, other type of synthesis. So the previous one is halogenation, halogenation of alkene, halogenation of alkane. In addition to that, we can also convert alcohol to alkyl halide. When you look at this, then when we are going to look further into the topic of alcohol, this will become the reactions of alcohol. You see how they are very interrelated. Now we are going to tackle this topic first, and you will see this topic again, or this explanation again, in the topic of alcohol reaction, precisely for alcohol. Okay, so alcohol react with variety of reagents to yield alkyl halide. So there are many reactants that you can use. Okay, the most commonly used reagent are hydrogen halide. So if you want, you have to see this one. Okay, essentially they are just substitution. Okay, we are going to substitute the OH here, the hydroxy there, to whatever halogen that we use here. If you use HBr, then over there it will become Br. Okay, if you use HCl, over there it will become Cl. In addition to using hydrogen halides, you may want to use what we call as phosphorus tribromide. You can also use phosphorus trichloride. Okay, PCl3, PCl5. Okay, where again, there's nothing else in the carbon, in the straight chain carbon. There will be nothing else but substitution of the OH here. That's it. Okay, just the substitution of OH to halogen atom. In this case, if it's using a Br, then we will get Br. Okay, you don't need to ether. Here is just a solvent. Okay, do not be confused by that. And there's no other thing that will play here. There's no other significant change. Even there's no change at all. Okay, the one changing is the OH hydroxy group will be transferred or substituted with Br. Okay, other than that, for Cl, you can use SOCl2, thionyl chloride, where alkyl halide from secondary and primary alcohol are synthesized from SOCl2. Now, SOCl2 is very direct. You will only Cl. Okay, you can only use Cl as halogen. Okay, there's no Br here. There's no SOBr2. Okay, for thionyl chloride, you have to make sure do not include the thionyl part. Okay, sometimes students confuse, they just put everything. Okay, what you do is you are going to convert the OH to Cl, and that's it. You see, even if the compound is quite huge here, benzoin, but there's no other things, other reaction for this compound. There's no reaction at benzene group. There's no reaction at ketone part, C double bond O. The only one that will take place is the substitution of OH. Now, whatever compound that we are going to throw at you, you are going to see that tidak balas or reaction will only occur at the one with the functional group related to the reactant. Okay, so over here we have C double bond O, but SOCl2 doesn't have any reaction to C double bond O. Therefore, the final product is this one only. Then we will look at the reaction of alkyl halide. Reaction of alkyl halide can take place in two ways. One is what we call as nucleophilic substitution, where you have nucleophile and you will substitute the halogen with the nucleophile that we use. Also, we can proceed the reaction of alkyl halide with elimination. So instead of substituting the halogen atom, we will eliminate both halogen and the hydrogen adjacent to the carbon with halogen, and we will have double bonds. So this is a summary of reactions of halogens where we have various nucleophile and reactant here. For example, you have halogen can be also, whatever halogen that we have can be transferred or changed into the new halogen atom if we react them with a nucleophile with halogen. We can also have alkyl halide reacting with H2O or OH minus that will produce alcohol. We can also produce ether from alkyl halide. Okay, now this is something that you are going to learn again, okay, in the topic of synthesis of ether. Okay, where we use alkoxide here. This is what we call as alkoxide reacting with alkyl halide, and you will get ether. In addition to that, alkyl halide also can be used to produce ester if we are reacting it with this particular ion. And a very good example again, for example here, reacting it with C triple bond N, you will get a cyanide there. Okay, now the further examples and mechanism of alkyl halide will be discussed in the live class. Thank you all.